Okay, so I want to give you we're going to go through a few of these images I have here. And I'll tell you what my agenda is, my goal to get you. Let's look at this column. And I want you to think of the pad on top. I've already put this in another video. I want you to think of the pad over top of the column. Reinforcement in this capacity. I want you to put in your mind that this is supposed to be all concrete and bonding the rebar to the concrete in the concrete pad. With that said, I want you to understand that this look is more of what it presents as bonding of concrete about there and about here. That this section in here is pretty much non-binding with the concrete. So if we look down here in this image, down here, let me back this up a bit now. And down here, rebar is on this side like that, and on this side, the rebar is over there, up to the top of the head. That rebar, looking at a closer image of it, I don't know where I can find it. If I can present it with you. That rebar presents as what I show you here, like that. Also has on this side of the column, it has a kink in it, so it looks like rebar and then a little bit of hickey, if you will, and then that. The hickey lines up with the top of the column head, of the pier head, of the head of it. It lines up there. So this, if I put this over here, that hickey, if you will, now let's go ahead and put it over here in a failed capacity, so let's do that. And what happens, you're getting rotation on this side and rotation on this side, opposite of each other. The deck's going down because of the dead load of the span between this column, let's say, and the column between here and the other one over here. And the distance, the loading of it, resolves itself in a butterfly, which we know to be about here. Remember, from this column to the next column also is what it has to take on the loading, and then the next one over to the control joint. Again, whether ACI tells you that you only can use 2 panels, or engineering typical agreeable situations, you go halfway over here and that goes to this column and it looks something like that. I say that's 100% wrong. It's a defect in the thinking. You don't get to do that, because the reaction, you just can't. This is not designed to be in a cantilever fashion, so you can't do the loads like that. But you should consider it in cantilever fashion, and consider this from cantilever cantilever action if you're going to be doing this breaking up stuff. But if you keep it together and you consider the whole bay, now you can evaluate the correct steel placement, etc. But now the argument is, oh, well, we're just talking about loads. Well, the load doesn't stop here. I can't just do that. I can't do the load back to here like that. It needs this other part of this pad for this to work. So this is dependent upon the other sections over here, here, and back to there, all the way to the wall. It's dependent upon that section, and this section here is dependent upon this section. This section is dependent upon where the cars are. They're all dependent upon each other. Let's think of what we thought they could do a war with Russia, and it was free. We could just sanction them. Turns out that no, they're part of the global economy, aren't they? I guess the powers that be didn't figure that out. So this is the same thing. It's all connected. You can't just use this old thinking of bays and loading of it. It's all stress. So if this starts going down over here, it's going to stress your section here more greatly. Deflection is where we're going to get this change of profile of the loading on the column heads. Okay, so deflection deflection. All right, deflection is where the change of profiling that we get up here, where you're going to get that release of the concrete bond. And this is probably done years ago, as I observed this rebar here up close, not in this image. It's rust between this section here, all rust. So it indicates that the hold that concrete together from the left to the right is done here at anchor points, anchor point and anchor point. And this rebar here, and having no paste bonding with it, it's acting like a bolt, if you will, and anchoring here and here. So here's the bolt head, here's the washer and nut on that side. And either side giving would allow it to start sliding in the concrete, slipping, if you will, in the concrete. And as you load it, the slipping will happen as the loading over the years go. So I state that the paste is what you look for on the rebar. And also in this case, when this went down, you would have seen grinding of the concrete from the rebar onto the rebar, and it would pick up the materials, and it would wind up at the rebar. This is rebar. It would wind up all the way down, and you would see white paste or grinding action taking. All I saw grinding were on the two ends. So two ends. This one, I'm sorry, correction, I don't see this one. This one I know is engaged though, because it's still holding on. This is the one I see the paste on. And my argument is that it's connected. It was only connecting on two ends. On the two ends. And the one that released, this is the one that stayed behind. It stayed connected to this deck over here. And the rebar goes up like that. So this is your release side. This is the side that was that released. Alright, and then we got the kink there. Your release side. Let me get you more data. Hold tight. Let me pause it and jump back in. It's going to be an instantaneous thing when I do it. So as we look at this view, there's the concrete I'm talking about. It's up. And we don't have that concrete up over here. This is just a different format. This is up, and the wire is holding it up, and it comes over to just slightly, not that far, way back here somewhere. And that tells me that this side is the releasing side. This side released. The deck sagged so much, and it slipped. It's allowed the rebar to slip through it and wind up going like that. But of course the rebar is like this right now. This is bonded to the existing concrete. I don't think this image will show it, but to the left, if I can pull out, maybe. I showed you in other videos that this one is the same. Oh, great. This one has the rebar also. This one here to your left, same deal. Not quite the same configuration. I've got to find it. I remember this. It's got like two antennas up. So it was engaged twice over here. Both are releasing. So the sag is over here, the release is over here, and then this goes down. All right, let's go from there. I will give you this in this video, is that I might do a little bit of a correction video. Over there on the far right, I can't see it. Far right, where the hinge, I talk about the hinge point of the planer box, and the hinge point being right there. It's a break, but upon further, deeper evaluation, there's a good chance that there's debris making that hinge point also. So let's just go back to that one. So that, in other words, I just always try to debunk myself, and to do that I need to get verification multiple ways of my thinking, and also see if I can debunk it, and I go from there. Now this one is my speculation that right about this plane here, about 5 tiles in, not counting the pavers, the edge, the border pavers, it's about parallel. So the deflection, I would theorize, would be somewhere between these two. And then looking to the right, I then try to see how it lines up. Well, it doesn't quite line up, does it? So let's do that. So remember I said I try to debunk. Lines up with the planter box. Okay. And then that's the columns, and then here's the middle. Well, that's the butterfly is down here though. It's not up here. Okay. So this doesn't work, does it? Doesn't quite work. So what do I think of? I just go back to the cars again. I keep in mind of all my rebar being pulled down. I want to do a video for you to show you these little, show you this over here. There's another one over here, another flap there. It was part of the asphalt, the stamped concrete. The rebar has a story to tell over there also. So this line continues over there about the planter box. So my guess is that, so that's one of our anchor points, and it's acting as a cantilever, if you will, from here. Pretty rigid. Let me put it that way. It's acting as a more rigid off the wall because of the rebar, and also because of how I'd show you the reactions. Remember, I put that piece of wood up for you, and then I run a piece of all thread through it. I also calls it thread all, and I piss off Embry. Apologies, Embry. Well, this back wall here and this concrete pad here, remember it has that force multiplier, but also it will act as a cantilever to some point right here. So the reinforcement and the rigidity of it will have some sticking off the wall. I would theorize it's about 5 feet on this one. Based on the fracture, I see a parallel to the butterfly. There's a parallel fracture to the butterfly, and it's up there. So as the butterfly goes down, let's do this now. So here's my 5 foot mark. Here is our butterfly, and now let's go up a little bit. So there's our 5 foot mark. Here's the other outside of the butterfly. Here's our butterfly, and here's our outside wall. So as it's trying to torque down, let's do the above it. I'm going to take some liberty here. I'm going to just run with it because I can. I'm going to do this. So it will be over here typically. But we have some rigidity off this wall, and I theorize it puts it off about 5 feet, which then moves this over to here. So our rotation is happening there upon these two fractures here. And then we get our shifting of the butterfly. That's what I theorize. It's the way I visualize it to account for the crack here. Of course, as it goes down, it snatches off the next piece. That's in the private video. You guys, please join. Come over there and join. I know some people don't want to join. Don't worry. I'll still keep giving you content. You're just going to miss the finer details. Although you could probably, if you got a good imagination, you could probably extrapolate from here. I talk about a fracture that's somewhere up here. It's pretty small. It's pretty darn small now. I've got a better imagery of that. Again, this is the flap. These got the two roach antennas sticking up. Yeah, that one. All right, pausing video and going to the next image. Okay, so here is the rebar with the paste on it. This image doesn't show well. This is the non-paste. There's other rebar on the other side of this. I think it goes down like that. It only stops there, not this. Something like that. And it's underneath the larger slab leaning against this up in this area. The slab itself has a break in it, and that tells you where how much it was engaged. It was able to fracture that part of the slab to get that to happen. Here's the steel. The steel we're looking at here is just near the outside of the shear head to allow for it to come to rest the way it is. Again, the paste is down here. No paste here, roughly to about there, and this is the part that comes over the head. All right, the other one has more of the hickey, as I call it, right? More the profile of how the deck was deflecting, I believe. So here's our deck over top of this. As our deck is deflecting multiple angles, four-way. Right. Steel reinforcement. I'm going to double down here now. Took on and this is in the concrete. And that one's in concrete. This is only our grip forces on the end. And again, this just acts as a bar. It can take deflection. It can't keep this concrete back together. Probably had some fractures here that were covered up by the overlay slab. Interesting. Tong Lee, 1996. I believe he's still in business. That company. Why wasn't he part of the lawsuit here? Did that report from Morbido? Did it give him a walk because he said no waterproofing in the original design? Because he didn't mention that Tong Lee put waterproofing there, and he didn't put it in the parking area, but he put it apparently not in the parking area, but over here in the swimming pool area and the pool deck area. So that's an interesting thing we have there, isn't it? Let's pause this. So this is the fracture we see by the parking car garage area, and you can see it's already indicating with the arrow. Look at the arrows. This is another movie I did, the post I did. You can also see the planer box is still present in that failure, and that's about the plane line of what's left behind. That fracture is about what's left behind after the collapse. So this fracture is a true indicator of a full break through the deck, what I call converging cracks, etc. That little nothing crack up top is an indicator of, well, loads this way, deflecting downwards. This didn't deflect downwards, just had that rigidity again off the wall. Remember off the wall? And remember the Dawn Lehman's supercomputer and herself and her PhD candidate all say it started at the wall there inside the gym area. Well, if that's the case, saying the wall with its reinforcement that sticks outside the wall is weak, the wall connection is weak, then how is it this planer box stayed behind? Starting at the gym area, why did the planer box stay behind? Well, or am I correct saying that they're supporting data, because there's no column under there, supporting data is this planer box and roughly about 5 feet off the wall gives it rigidity the way it's anchored in this effect here. This is something that I educate and teach, but this is not something ACI even knows about. I would love ACI to contact me and update their whole, belief on how concrete behaves. But I am sure that my behavior of concrete is supported by all my testing, that this is true. And even in this collapse, it verifies its rigidity. The deck, all that going down there, including the entire building, and yet that planer box says stays put. Because those fractures are not for free. I tell everybody that cracks are not for free. They all mean something. This crack created a shear plane. All right, it created a control joint that allowed for breaking and not developing itself all the way over to the structure, over to behind the planer box. Now let me pause this and move on to the next one. Okay, so here we're looking at the gym area, and there's the door, and there's the palm tree I point out in one of the other videos. Entrance to the gym, you walk up some steps, you wind up at this elevation. As you can see, it appears to have a block wall and then glass, small section of glass to your, section of glass to your left as we face it. That would be to the west. To the right of that, we see pretty much solid systems here. This all appears to be solid until you get over to 111. So, until you get over to 111, there's the parking area. There's a bumper. Okay, so a bumper, planter box, elevated planter box, and this will be why you see asphalt higher up on the column over there and kind of like bare concrete here, because you're looking at an elevated planter box to the right and then a lowered planter box to the left. Remember I said I think they had planter boxes all low at one time, and I was trying to explain for that in the video, the one I did the narrative over Josh's video about why the cracks. Supporting that data that I think it was low boxes at one time would be this planter box here. Look at the low height. And then perhaps on the other ones, this one they went with rail. And with the other ones, they went with planter blocks and large shrubbery. So this shows that the planter boxes there were some low planter boxes at this location. So now looking at the drawing here, I'm going to line these up. It's only a little slight offset, like 6 inches right on that first one I just went past, and out to here. And then I'll line these up, and they've got a 8-10 inch offset, and these guys go the other direction, right? This one goes the other direction like this. I won't line those up. So here is our unsupported span here, pretty much, and then an unsupported span back to here, back by the wall, of course. This is where I said I get to come up about 5 feet and go with rigidity, and that's all the way over there, and I get to push that there. Remember, there's a fire department hose, or whatever ventilation or fire department hose, venting hose right about there somewhere. Did I put it in the wrong spot? Yeah, it's right about there, right? Anyway, that circle, this one. So that gives us a break, and the reaction's a little differently also. But and I talk about how the rotation of this box here happens in another video. It's so simple once you see it. So now we have our butterfly here, though. Our butterfly deck failure right about there. So now the center line from these two, I now get to find a working center line closer to that, maybe there. But if I go from this one, this is almost 2/3 over. But hold on, wait for it. Let me get rid of it. But because, let's put the circle back. There are columns here. That's a column head. Column head. Is it a column head right here? Column head. Column head. I did another more complicated version of this. Remember, the triangular array creates this torque action. It's sort of like all bets are off, or almost, with the way I did it. Now, but these in line, well, they act like a nice shear plane. But this thing up on this side, this is just a torque nightmare. And this is the one right here where we have the head like that. The one back here, I think, is the same. So it's telling you that the deflection is greater on this side, weaker on that side to the right. And it duplicates. It's starting to duplicate now, like this and this on the other side of the column. Making me think now about construction details about them doing it. Did they inherently pull down the forms a certain way to cause the bond break? Remember, I have a bias about bond break in the rebar. You won't get deflection, if you won't get the cracks if you don't lose a bond break. You'll stay engaged. You don't necessarily need to see the concrete crack for the rebar to be active. It has a rigidity to it once it makes the concrete to be in there. Now, most people will tell you that, well, when it's just cracked, though, it is active. But it's a rigidity also that's created, like a internal beam, if you will, top and bottom steel. And I don't want to give this away. No, I'm not going to give that away. That's part of my ACI debunk videos and showing how concrete really behaves, which I already showed with that one video here, like this, right? You got to find it. Column here, rebar there. Out you go. Okay. So we get this. I just showed you that, and over here we also have the rebar like that. So I mean, the reinforcement. So it's consistent with this side being the loose side that gives loose from the reinforcement all the way over. This is the consistent mapping that I'm seeing. If we look at the columns here, we see that they've been stripped down also. The rebar didn't pop. It gave way. It slipped away from the concrete. I don't see popped rebar anywhere over here. or here. Maybe there's an elongated one over there. Maybe there's one that was stretched a bit before it popped. But they're tails, they're things that stay out, tail, and they're all about the same length. And this one on this column here is significantly long, whips out like that, showing you that the engagement is still engaged in the column. The column held it, but where it didn't hold was out in the loaded area where the cars kept loading it, cycling it. That and then the covering of the overlay allow for non-visual inspection. It reminds me of the bridge, the chain link bridges, the one in Ohio that went down. The link bridges, they can't really repair them because they don't know how to transfer the loads and replace a link, an I-bar. So this reminds me of that. You cover over the deck, you can't see the brakes in the deck, but you can see the brakes in the ceiling down below. And that's where I tell you the tributary area is like this. It's where the cars were, where their pipe were. The cracks developed towards each one of these columns. They're our biggest indicator of deflection of the deck, and they point towards where? Right to the tributary area. So deflection there gets you so stressed back here, which we see 3 weeks before. This one really identified itself. And the person came out and said it was grass. I'm sorry, it was roots. I find that to be very odd. But with that said, I did a video and I showed you the underside of this box, and I showed you greenery growing through that video. But these are very light shrubs of light roots. They're not the roots that have the ability to expand and break up 12-inch cinder blocks. I believe they're 12-inch cinder blocks. They don't have that ability to do that. So, and the soil was a good drainage soil. It had stone in the bottom of the boxes, so the water was making its way out. Let's go out of this. Let's pause this. I'm going to give you a couple more things. So I'm going to give you this one. Look at the orange arrow. That's that reinforcement I talked about with the long tails. And these guys right here. That they don't, they didn't break here. It just slipped out from the concrete. So the deflection was taking place and the bond break took place a long time ago. And it's consistent with the on front of 72, the two long whips down. Antenna road chairs when I see them pointed up, and I guess I call them whips going down. These little whips. Oh, I don't mean like a whip. I mean like electrical whip, actually, is what I was thinking. Not like a whip, like as in, not like that. But I guess that would work. Not really. I'm thinking electrical whip. I own that right now myself. So there's two more, right? And it looks like it's missing a couple bars there that might have popped off. And I base that over here to the left, to the right here. We see the two bars here with their little tails. See them? They're turned out 90s. And back here is where I pointed at the other image, where I talk about that crack means something. Where we look at the top view down, there's the planter box. That's about where the crack was. And that is my 5 foot approximately rigidity off the wall. Which back here when we look at it, there's some floor breaking down there by the gym area, but that was also loaded by the shear wall coming all the way over from the other side of the building and driving down on top of it too, like a knife. And that also caused some more damage over there. So I'm talking about that fracture there. The fracture, I don't know how new it is, but we don't see any water bleeding through it and things like that, but it probably did have some water coming in. But I want you to look at that column there, and that's deflection, indicating of deflection, and deflection will be here. So between this one and that one that the engineer came out and inspected, the one to the right, okay, we can barely see it right here. And so that there's our loading of it. So it loads there and it loads from here, and we get this deflection. And we get that steel like that off of this one. Okay. Let's see what else I got here. Yeah, that's what I'm talking about there. That's that whole panel that came over. Um, that's about where the location is, what I'm stating there. The way twist. Where's the planter box and palm tree, which is located outside of gym? Okay, there's a palm tree there, is what I'm saying, in a planter box. It's better in the video I made. So I believe this is the palm tree here. I think it is. It's in a video much more clearly. The video I made on this palm tree deal. And then there's the gym over there, and there's the behind the column, the other one. Let me pause it. So I want to bring your attention to the elevation in here. I've gone over these elevations a couple of times now. It's noteworthy to note that the drain, approximately 9.5, not approximately, it's at 9.5, 9.5 feet. Over to your right of that is the 971 right here. That's where the cracked box appeared. See 971? Over here is 972. So these are the same elevation pretty much. This one here and this one here. Here is the column, which we know probably pretty much stationary, 963. But we have a 954 here. It's a dip in the deck at that location. And then there's a dip between here down up to here. The dip's there, but the water would then go in this direction. So it's almost, the dip works as water runoff and not as a, because we don't know what it was as built after they did the original Tong Lee. We don't know his as-built. I try to find him. Now that says 972 I showed you. Now watch, I show you. Let's zoom out. There we go. So this is 971 and this is 971. So there's the same elevation. Core sample was somewhere about here. But they go to here and to here elevations. That's 963. Now I'm not saying the 6.3 lower down at all. It's out here in a tributary, just a little bit into the tributary area. Not, I would say this is the columns over here. This is full tributary here, but nevertheless, it's there. And there's a 959. There's a 957, but it's higher than 950. So their intent might be just to run the water there. But this one is definitely the arid one, the 954 here, and then you go into a 963 that has a tendency not to get over 963. So here's a 959 here. You see, you can't get beyond that because everything is higher. It's a 963. It's surrounded by higher numbers, so this will be a pooling water until it can overflow and make it up to the 959 over here. And then it would be over here, it's flat, so it would be a big pool area. And then it would then go to, let's see what's next, 963. So then the water would pool like this. It's open. And then once it breaks to 963, it's done. Once it crests to 963, the water level, it would then roll towards the drain, and the rest of the water would be standing water to have to come off just naturally. 2-3 days or whatever it may be. 2 days max, I would hope. This one I can't quite make out. That one I can't make out. Looks like a 9.6 something. I don't know. Alright, so here's your 971. Here's your 971. And there's your drain, 950. All of this works its way to the drain. I looked at that. It all makes its way to the drain, with the exception, like I said, of if you map it, it looks kind of weird. Like this. So that's 953. Oh no, it's 953. I see it now. I thought there was something there. So that actually wants to do that. 953 being the lowest. It wants to sit here, then flood into the 954, then the 959, then the 963, 959 might roll over to the 957 over here, like that. I forget what's over there. But then this again, once you crest the 963, she'll go towards the drain. I'm not going to waste your energy on that. I did already, but let's just jump out of that. Just want you to take note of that. I'm going to end this video because it's getting long with this one. There's a piece of steel. Do you see it right here? I'm going to move it away. And do you see it? Put it back there again. Right there where it is. I'm going to remove it. And that's the steel I'm talking about. And this is this slab here was up here at one time. The steel was engaged on that side. Lost the engagement. This side is stayed engaged with. This is the side it deflected more. Once it released, this head can't stay up there by itself. This deck couldn't stay up there by itself. It got pulled down with the extra loading on it, with the extra bars going across. But, you know, there we go. And it pulls it down, and we get that rebar like that. So that's the rebar that I talk about. So our deflections over here, or you can clearly see your releases on that side. This side is still engaged. I was able to fracture the pad. Fracture the pad right about there, the top pad. So Long Lee was the engineer that did this whole topping. Why is he getting a pass? Why is he getting a pass? Why? How come I don't see him in any of the suits? Here's that 5 foot I talk about, right about approximately there, going across. See some shifted tile here. There's our butterfly. The gates look great. They did the evaluation of the gates. They opened and closed with the fireman there pretty much. They blocked it with a hose. We have a little daylight here you can see through. There's our spacing down here. So that's about the size of this. What am I missing there to show you? Fractured box, cantilever. Whoops, back here. Yep. Okay, love you guys. Bye.